Section 3.2, linear functions. Okay, we're going to start with a vocabulary term, linear equation in two variables. Basically, that means it's an equation that can be written in the form y equals mx plus b. Now, you should recognize y equals mx plus b is slope-intercept form. We'll get to slope-intercept form in a later section, but any equation that is a linear equation can be rewritten in that form, y equals mx plus b. And they call it a linear equation because, well, the graph forms a line, and the first four letters of linear spell out the word line. Okay, so we've got two different types of functions that we're going to be working with. We've got linear functions, which are functions whose graph is a non-vertical line. Non-vertical just basically means everything but vertical. Vertical is straight up and down. And then we're going to be talking about, well, not so much in this section or even in Algebra 1 really, nonlinear functions is any function whose graph is not a line, which makes sense. Nonlinear means not a line. Okay, so what does it mean to be linear? Well, it means the graph is a line, number one, and then number two, there's a constant rate of change between x and y, okay? And I've got a couple examples here to kind of represent or to show you the constant rate of change between x and y. So the examples here, does the table represent a linear or nonlinear function? And if it's going to be linear, then the key part here is a constant rate of change, okay? So for number one here, to go from 3 to 6, that would be up 3 or plus 3. From 6 to 9, plus 3 again. From 9 to 12, again, plus 3. Okay, if we go look at the y values, from 36 to 30, that's down 6. 30 to 24, down 6 again. 24 to 18, also down 6. So what we've got here, while the numbers aren't the same, they are the same from each x to the next, and then the same with the y's. These numbers themselves don't have to be the same, but these numbers have to be the same, going from left to right, both the x's and the y's. So number one here, this one is a linear function. Okay, number two, let's see, we did the x's in red, so we'll go back to red. From 1 to 3, that's up 2. From 3 to 5, also up 2. 5 to 7, up 2. So we're promising, we have a promising start here for our x values. They are all the same. Let's go take a look at the y's. From 2 to 9, that would be up 7. From 9 to 20, that's up 11, and from 20 to 35, that's up 15. So while we had the constant change in x's, we don't have it in y's. So this one here, number 2, would be an example of a non-linear function. Hopefully you can see the difference between constant rate of change up here and a non-constant rate of change, or an inconsistent rate of change. Okay, it's not the same from each ordered pair. All right, let's move on to the big part of the section, graphing linear functions. I got a lot of writing here on this page, but it's a lot of vocabulary and then some important information. So the first vocabulary term is solution, and any solution is just an ordered pair x, y. That's how ordered pairs are written, x comma y, that makes an equation true. Okay, so why that's important is that we need solutions or ordered pairs in order to graph functions. And when we're graphing functions, what we're actually doing are plotting solutions of the equations. That's what we're really doing. Okay, and we've got two different types of domain. Remember, domain from section 1 is all the input values. Okay, so we've got two different types. We've got discrete domain and we have continuous domain. All right, so the difference. Discrete domain is a set of input values that consist of certain numbers in an interval. For example, the integers between 1 and 5, which would be 1, 2, 3, 4, and 5. These are like things you can count. So I'm going to write countable right next to the example, right underneath the definition, okay? Discrete domain is something you can count, like integers or tickets or bottles or balls or dollars or something like that. It's something you can count. Whereas a continuous domain, the second type of domain, is a set of values that consists of all numbers in an interval. So for an example, all numbers between 1 and 5. How we would write that would be 1 less than or equal to x less than or equal to 5. There's no way you could list out every number between 1 and 5 because you would miss one. There's no doubt about it that you would miss one. There's so many decimal places. There's an infinite number of decimal places that there's no way you could list out every number between 1 and 5. It's just not possible. You can't even list out every number between 1 and 2. It's just not possible. Okay? So that would be an example of a continuous domain. It's not something you can count, okay? Whereas discrete domain is something you can count. All right, so the steps for graphing. Number one, determine if it's linear. And the question there is, can it be written in the form y equals mx plus b? If the answer is yes, then we can move on to the next step where we make an xy table to find ordered pairs, plot the points, and then if the domain is continuous, we're going to draw a line. Because if the domain is continuous, that means there's more points on the graph than just what we put on the graph. And that's where the line comes in. Rather than try to plot every point on the graph, what happens is we end up making a line anyway, so we can kind of make a little shortcut by making the line and not having to plot every single possible point on the graph. Because if we did and then took a step back, what we would do, or what we'd end up seeing, is in fact a line. All right, so let's try an example here. The linear function y equals 1.25x represents the cost y in dollars of x bottles of orange juice. Each customer can buy a maximum of 5 bottles. All right, so number one, find the domain. Is it discrete or continuous? Let's start with the second part. Is it discrete or continuous? Can you buy, for example, half a bottle, or a fourth of a bottle, or a third of a bottle? The answer there is no. Okay, this is something we can count. We can put physical bottles in our cart or in our basket. So this one is a discrete domain. Whoops, let me spell that correctly. Discrete. It's a discrete domain because we can't buy a half bottle. It's not possible. Okay, the store's not going to let us cut the bottle in half or pour out half a bottle. Okay, it's a discrete domain because we can't buy a half of a bottle. Okay, so then the domain, in fact, let's list it out here, the domain. So it says we can buy a maximum of 5 bottles. What's the minimum number? Well, we don't have to buy any bottles. So the minimum number here is 0. So the domain is going to be 0, or we could buy 1, we could buy 2, we could buy 3, we could buy 4, and we can buy a maximum of 5 bottles. So we've got a 6 value, or there's 6 numbers in our domain. Okay, so obviously this one's linear. It's y equals mx. There's no b in this case, but that's okay. So we can actually go ahead and graph this. Before we can graph it, though, we need some ordered pairs. Okay, so I'm going to have x, I'm going to have y. I've already got my x values. That's the domain. Okay, so I'm going to get rid of that line. So we got 0, 1, 2, 3, 4, and 5. Okay, if I buy 0 bottles, remember we're using this function right here, y equals 1.25x. So that'd be the cost y of x bottles. So if I buy 0 bottles, my cost obviously going to be $0. If I buy 1 bottle, that would be $1.25. If I buy 2 bottles, that is $2.50. And again, if you're not sure how to find the y values, just plug and chug. Take these x values right here, put them in your equation right there for x. Take your x value times 1.25, and that will give you your y value. Okay, so for 3 bottles, 1.25 times 3, $1.25 times 3 is $3.75. 4 bottles would be $5, and then 5 bottles would be $6.25. Let me rewrite that 5. That's a really bad 5. $6.25. Okay, so now let me bring in some graph paper here. Let's see if we can't actually go ahead and graph this. All right, so there's my x, or my y coordinate, my x's. Let me slide those up a little more. 1, 2, 3, 4, 5. Okay, so we'll have 0, 2, 4. And then let's see, we'll go 1, 2, 3, 4, 5, 6, and we'll have to go a little higher. That's okay. So we got 0, 0. Let me label my y values here. 1, 2, 3, 4, 5, 6 is up here. Okay, so we have 0, 0. We have 1, 125, so that's right about there. We have 2, 250, which is right there. 3, 375, which is right in there. Whoops, I missed the line, didn't I? Oh, no, I didn't. I just put this point in the wrong spot. 2, 250 is there. And then 3, 375. 4, $5 is, let's see, 4, and $5 is there. And then 5, 6 1/4 is right in there. Okay, so obviously you can see the points make a line. We're not going to draw the line between them because we said we have a discrete domain. We can't buy half a bottle. Okay, we're not going to have extra points in between these that would help us make our line. Okay, so we just have the red marks. We don't need the green ones because it's a discrete domain. We can't buy a third of a bottle or a half of a bottle or a quarter of a bottle or anything like that. Okay, so it's just going to be those 6 points on the graph. All right, let's do an example of a continuous domain. All right, so a runner's speed is 5 miles per hour. The number m of miles run is the function of the number h of hours spent running. So question number 1, is the function linear? Well, what that means is the answer here is yes. It's linear because as h goes up by 1, so as the number of hours increases by 1, the miles goes up by 5, okay, because it says the runner's speed is 5 miles per hour. So if I run for 1 hour, that means I went 5 miles. Okay, if you add another hour, you go up 5 more miles. So it is a constant rate of change. We have a linear function. Okay, number 2, find the domain. Is it discrete or continuous? This one I would argue is continuous. Okay, continuous. The reason it is continuous is because we can't count the number of hours. We could have a half of an hour, or a quarter of an hour, or a third of an hour, or 1/100th of an hour. Okay, this is continuous because we don't have to be whole hours. Don't have to be whole hours. Okay, our hours don't have to be whole numbers or even half numbers. You could have, you can come up with an infinite number of different hours. Okay, it might be the difference of a half of a second or a quarter of a second, but it is different. So what we can say is then that the domain itself is h is greater than or equal to 0. The smallest amount of time spent running would be 0 hours, and then you can have anything more than that. Are you going to run for 40 hours? Probably not, but you could. So that's why we have to say h is greater than or equal to 0. And then step number 3, graph the function. All right, so since we have a continuous domain, let's just pick some h values. Okay, so we'll have h, we'll have m, and let's just pick, say, 4. So let's say 0 hours, 1 hour, 2 hours, and 3 hours. Okay, so if I run for 0 hours, how far did I go? That would be 0 miles. If I run for 0 hours, that means I go nowhere. I ran 0 miles. If I run for 1 hour, the problem says the number of miles run is a function of numbers h spent running. So if I'm going 5 miles per hour and I go for 1 hour, that means I've run 5 miles. If I continue that pace and I go for 2 hours, that would be 10 miles. And if I continue the pace for another hour, that would be 15 miles run. So I have 4 ordered pairs that I can graph here. So let me put these up here. Okay, so I've got 1, 2, 3, 1, 2, 3, 0 is here, and then we'll go 5, 10, 15, and then 20 would be there. 5, 10, 15, and let's put these on the graph. So we got 0, 0. For 1 hour, we would go 5 miles. 2 hours gives us 10 miles. 3 hours gives us 15 miles. Now, since this is continuous, obviously we could have a half hour, we could have 1/3 of an hour, we could have 1/100th of an hour. It doesn't really matter. But what it means is that we need to actually draw the line. There are so many more points in between those ones that we marked that if we were to possibly graph them all and then take a step back, what we would see is a line connecting all of them, or what it would look like is a line. And make sure that you have an arrow on the end of your line to show that the pattern would continue.